Okay, now let's start some advanced problems on fundamental theorem part 1, and I described the theorem in detail in the previous video. So if you need some basic understanding, I recommend you to go through the previous one. Okay, right. So let's start with this problem. Now here they have given a very complicated looking function, and this function is a function of x, right? And then we are supposed to find the derivative of that function, right? That means the derivative of g with respect to x, right? Now simply we should apply the derivative rules, but that's all we can do, right? Now since we have an addition in between the terms, we can consider this whole thing as an addition of two functions. If I name them as let's say h1x and h2x, right? So as gx, what we have is h1x plus h2x, right? And as we have that, and when we are supposed to differentiate this given expression, what we can do is g prime x will be equal to, this comes from the derivative rules, right? h1 prime x plus h2 prime x, right? Okay, how about h2 prime x? Here we have h2 as this one, and from the derivative rules we can say that the derivative of arc sine x will be equal to 1 over 1 minus x squared over square root, when this is the derivative of arc sine x, and this is the derivative of arc sine x. But when you have x squared, you will get 4 here, and from the chain rule part you will get 2x here, right? This is the chain rule of differentiation, right? Okay, so we know the answer for this one, which is 1 over 1 minus x to the power 4 square root times 2x, right? And how about this one? See, now this is the place where we can use the fundamental theorem. Now as h1, what we have is this, right? 1 minus t squared square root dt, right? And simply what we have to do is we just have to differentiate this thing, right? From the fundamental theorem at once. Now see, this goes with the statement of the fundamental theorem. So at once we can say h prime x is equal to sine x over 1 minus x squared. That comes from the fundamental theorem, right? Okay. Right. Now let's see what about this function. Now although it looks like a simple expression, there is a subtle point in here. Obviously this is a statement or a question where we have to use the fundamental theorem, right? Because it satisfies the format except at a single place, right? Now see, in the original expression of the fundamental theorem, you have x in place of the upper limit, right? But in here it is not particularly x, right? It is 5x, but this is a function of x. So according to the theorem, if it is a function of x, you must have x in the upper limit, not anything else. Even you cannot multiply it with the simple constant, right? So how can we alterate this problem, or how can we make some changes to this problem in a way that we can use the fundamental theorem. Here again we can use the chain rule. Now see, in the fundamental theorem we can rephrase the fundamental theorem like this. Okay, now when you have a function t dt, instead of writing it as gx and writing the derivative, if I directly write this one, right, instead of writing it as a separate function and then computing the derivative like g derivative of dgx with respect to x, instead of writing it like that, if we directly use this notation, we can again say that the answer is equal to fx, right? Okay, so accordingly, how can we do this problem? Now see, the important point that I want to highlight is you should have the same variable notations in here as well as in the upper limit. So in this case, as we are to find the derivative of kx, that means the derivative of k with respect to x, we should find the derivative of this thing with respect to x, but here you have 5x, right? So what we can do is we can make use of the chain rule, right? So what we can do is we can write this one the same thing, and here the original problem was this one, and to apply the fundamental theorem we should have d5x term in the differentiating notion, right? So from the chain rule, if we have this one, to counterbalance it we must have this. Now this comes from the chain rule, right? Now these derivative terms are not multiplications, right? But if you just consider them as a multiplication, you can like visualize some sort of a cancellation like this, and you will end up with the same initial problem. So we have not made any changes, instead we have applied the chain rule, right? Then as we have this one, it is of course the statement in fundamental theorem, right? So accordingly it is a function of, now here in the initial stage it was a function of x. Now this was a function of 5x. You can even consider this as a single term u, right? You can even visualize it like this, right? So this will be from the fundamental theorem, it will be u cube times this one 5, right? This comes from the fundamental theorem, and this part comes from the chain rule. Derivative of 5x with respect to x is equal to 5, and here you can resubstitute the original terminology, right? Because u is equal to 5x, right? So you don't have to do all these things, I just did it for the sake of explaining. You can directly apply the chain rule for this point itself and then just come up with the direct answer, which is, now since this is a function of 5x, this becomes 5x along with this function and times 5 for the chain rule part. Okay, right. Okay, the part C is also the same as the previous problem that we discussed. We have to compute the derivative of fx with respect to x. That means we should compute the derivative of this term. And this is not exactly the statement of fundamental theorem, but instead we can use the chain rule and have the proper fundamental theorem statement, right? 70 dt times d 4x cube over dx, right? Now this goes with the fundamental theorem statement. The same variable you have here is mentioned in the upper limit, and then from the fundamental theorem it says instead of t, now this is a function of t, and from the fundamental theorem you will have the same function but with the appropriate upper variable, right? So this becomes 4x cube times this, when you differentiate this term it will be 12x squared. Okay, right. Well, I think in the worksheet they have this one as 4x squared, but I did the problem for 4x cube, so you can do the 4x squared part in the same way. Right, now let's go to the next question. Here we have to find the derivative of this function given like this. Now first there's one thing that I want to highlight. Don't get confused with the variable names that they are using in these cases, right? Now say for example in the previous problems the function inside the integral is defined in terms of t, and the limits, the upper limits basically were given in terms of x, right? But in this case the inside function is given in terms of s and the limit is given in terms of t. So there is no such importance of the name of the variable that we are using. They are basically called dummy variables. They are used as dummies, right? So only thing is that you have to clearly identify and separate them out. Now, like s is used to integrate this one, and t's are used with the upper limits. Basically they are associated with the outer function, right? Okay, now here we cannot directly apply the fundamental theorem. There are two reasons why we cannot apply the fundamental theorem, because at first we don't have a single variable. Now since this is a function of t, to apply the fundamental theorem you should have t in here, and also you should have a constant in the lower limit, right? So there are two factors that obstruct us to apply the fundamental theorem, right? So we should get rid of these two things as well to apply the fundamental theorem, right? Okay, now for that let me explain you some basic result in integration. Now say if we have a function like this, the integral of this function in this within these 2 points. So basically what do we mean by an integral? That means the area under this curve in between these 2 points, right? So if we have c in the middle, we can even write the integral as the addition of the areas of these two separate regions. That means the area from A to C plus area from C to B will be equal to the area from A to B. That's basically we have this result, right? A to C plus C to B, right? But here C was in between A and B, right? So then if you consider the notion of area, this comes as a very obvious result, right? But this is not the only case we can have this sort of a relationship, right? We can prove, but we are not going to do it in this video. We can prove that whatever the numbers we have like this, the order doesn't matter, right? Like A can be in between B and C, C can be between A and B, or even B can be between A and C, right? That order doesn't matter, right? Whatever the order of these numbers is, we can still write the integral like this, right? So whatever the order we have, we can still write it like this. That means we can use a relationship of this format, or else we can use something like, let's say, B and C. You can write a number in between and write it like this, right? The only requirement is you have to use a third number, a third letter. It need not to be in between B and C. It can be just any sort of a number. We can prove that result, but we are not going to do it. So you can use any number, and the only requirement is here it should be the upper limit and here it should be the lower limit, right? So the same corresponding result when you consider the area and a point in between, you have this result, and there is a corresponding result for the integrals for any order of these letters or numbers, right? The only requirement is the first integral should start with the original lower limit, and the last integral should end with the original upper limit, and there can be any sort of a number in between, and this number need not to be in between these two original lower limit and upper limits, right? And this knowledge will be useful to compute this one. Why is that? We can write the given function with a 0 in between, right? So we can write the function qt like this. Starting from t ends at 0, and you have the function ln s squared plus 0 to 2t. See, this is the thing that I explained before, and you can see that the location of 0 does not play an important role in here. Only the requirement is the lower limit should match with the lower limit of the first integral, upper limit should match with the upper limit of the second integral, and the same number should be used across these two integrals, right? And this number need not to be in between t and 2t, right? Okay. Now, as we have reduced down to our initial function into these two formats, we can apply the fundamental theorem, okay? And if we need to differentiate this one, that means we have to differentiate this one and then differentiate this one. And if you consider the first term, we can apply the fundamental theorem, but again there's another one more additional requirement that we should have, which is you should have the variable as the upper limit. So what we can do is we can write down the same thing with a negative sign, right? When you multiply with the negative sign, everything will, like the two limits will interchange, right? These are derivatives of ds, okay? So as we multiply it with negative, it becomes 0t. I recommend you to watch the previous videos as well, right? In order to understand the fundamental theorem in detail, okay? So as we have this one, we can directly apply the fundamental theorem, here you have now this entire thing you have to consider as Fs, right? And this will be Ft from the fundamental theorem plus, and for this one you have t here, a constant here, that is okay, but in the upper limit you have 2t. So you cannot very directly apply the fundamental theorem, you can't do that, but you can make use of the chain rule to have the same upper limit as the differentiating variable, but to counterbalance it, you have to apply the chain rule once again, because it's like we are introducing a new variable here, right? But the thing is, we cannot change the original problem. So to counterbalance it, we have to have a chain rule term associated with this new variable. So these two will get, like, it seems like they are getting cancels out. That's the nature of the chain rule. Okay, so from this one, it's a direct application. This will become a direct application of the chain rule. So here you will have f of 2t times derivative of 2t with respect to t is 2. And here, since fs is this one, ft will be, don't forget the negative sign. Now for f, I am including the negative sign also. And then it becomes negative 4 times ln plus t squared. And this negative is for all the terms. And plus f of 2t. So here instead of s, you should have 2t, right? 2t squared, this whole thing multiplied with 2. And accordingly, the last problem is somewhat easier than the previous ones that we discussed. But the only confusion that can come is with these variable names, right? Now, because normally we use x as the variable that we have in the outer function, right? Like this. But here, they have changed the names of those variables. For the inside function, we have it in terms of x. That means the integral runs through the variable x. And for the variables as the limits, they are using the name t. So my advice is, do not give some unnecessary values for like the unnecessary priority considerations for these variable names. They are just dummy variables. You can use whatever the letters that you prefer for these variable names, right? So given that it's just a simple, now it's a simple application of the chain rule, the fundamental theorem. So basically you just have to differentiate this thing, right? So for the first one, you can directly use the fundamental theorem. So this becomes t to the power t. And for this one, as you have a variable in the lower limit, you cannot directly apply, but instead you can multiply it with a negative term. And then it becomes, when it is multiplied with the negative term, it becomes 2t dx. But here, of course, as you have a negative outside, like you have anyway, you have a negative term outside the integral. So along with this negative sign, you can take it out and this becomes positive. So then you can have the fundamental theorem for this one as well, right? That's all for today, and let's meet on the next week.